you can start. Yeah.
All right. So, well, first, thanks for having me here. And probably you cannot guess what I'm going to talk about today by the title that I have here. But I have put a little bit of insights if you see the change of colors from blue to the green. AI brain machines building useful intelligence systems for science. When I'm thinking about machine learning or AI, we tend to focus a lot on technicality, and we somehow missed maybe some of those useful goals or aspects that we want these frameworks to have. So I'm an electrical engineer and I work on machine learning, and every now and then I try to remind myself that we need to talk to those that are not doing machine learning research for us to be able to remind ourselves that these tools are going to be used in society, in healthcare, probably in our some future years of justice systems and all. So what are the challenges that we might be facing today is I want to talk about, and then briefly, I'm really a fan of brain, so briefly take you into the journey of if we look into an algorithmic way of how the brain works, we might be able to resolve those AI challenges. So, all right, spoilers from the first title. So when we talk about AI, we want them to be useful. So what useful means? So what is a useful tool or technology for us? I want at least one answer maybe, so I can help here as well.
A laptop or a television.
Mm-hmm. So they're providing, for example, some resources that maybe we couldn't do by our hand. An example here, I'm bringing a microscope, so it allowed us to see things that are small at a scale that were not possible before, or we can thinking about how, by the way, I'm using the notion of tools not very strictly, so tools have a particular definition, but we can thinking about cars that they do have a goal. So they want to take us from one place to another place faster and safe. So we can thinking about that, or we can move on. There are a variety of things that we are nowadays using, and another one that comes is indeed systems that are doing a lot of automations for us, and generally they're in the category of AIs. So although probably a lot of the talks and majority of researchers, when they start in their talks, they tend to skip some of these definitions that we're going to go through, but I believe it's important for us to be able to have maybe keywords that I'm putting here to make your life easier. You don't have to invent all, such that we want these tools to be safe. So the car needs to be safe. We want them to be reliable, such that if they're showing us images today, they're going to show the same image tomorrow and the day after, such that we can rely them in the long term. Not that they're going to fail if you move a technology from Canada to Europe and then they say, sorry, we only specialized it for the human being in North America. So here I'm dropping some keywords that some of them are technical maybe and some of them are non-technical. So a few of those I'm going to touch on, like is the notion of generalization. We want any AI systems to be generalizable. What I mean by that is you want a system to be able to be widely used and to show certain performance guarantees. You can think about it that before the era of artificial intelligence, electrical engineers were designing MRI technologies based on some developed models for physics, how magnetic works, and perhaps without us looking into them, they had some performance guarantees for us to know for how long these patients need to go and how many measurements you need to take, such that you guarantee certain level of quality of the imaging that you get from the brain. And as AI framework comes, some of the other words become important in a sense that we want these systems to be understandable and interpretable, and I will touch on that a little bit more. Probably the microscope, if you know some things about optics and all those, it might be easier for the society to accept them and as a framework that we may not understand every single detail, but there at least exists an expert in the society that understands, so we rely on them. But AI frameworks, they may not usually work logically and interpretable. So today I'm not going to focus on this acceleration because we all know that AI has changed a lot of things for us to be able to, for example, do things faster and such. I want to focus a little bit more on some other aspects that indeed we are challenged by and the society demands it in those. Okay. We looked into keywords for usefulness, but in order to take it further, probably we do need to dive into what do we do in science. So what is the process? Let's say you're a scientist and you would like to go through 4 to 5 steps of studying a phenomenon.
Develop a hypothesis, design an experiment, run the experiment, analyze your data, and then reassess and kind of come back to the beginning.
Yes, very good. So you probably an expert on that, so I put some 5 steps, and there might be interchanging with, but let's bear with me on that. So we do observations, so we collect data, and as you mentioned, so I'm not an engineer, but let's assume I'm also a scientist. So we take and hold some hypotheses and try to create some models. As an example, you can thinking about in the brain, you can model how the neurons are firing with some basics of some differential equations or an electric circuit model of that. And then trying to see how that model is explaining the observations that you have got. And given that, we go through the process of, if you're trying to better understand the system, I'm calling it in this case inferring. So you're trying to infer, for example, what are the causes of that disease, what is the brain function and such, and hoping that through this process, your understandings are going to bring certain principles that will be lasting and generalized, such that you can, for example, write an equation and give it to someone else in 20 years and say, this is how we think imaging from the brain, and this is how we think this particular disease is propagating in certain new environment. Probably I agree with you that these steps that I put here are very clear from the perspective of we as a human and scientists, but the reason that I have put it here is the way we design AI systems are not following these steps. And I believe this is the reason that we are missing some of those properties. Okay, so going back to the tools that we had, there are certain tools that has been developed over the years that has helped us to have better observations for these steps of the science. Some tools have helped computers, for example, to be able to perform the simulations, as you mentioned, and models to accelerate and solve optimizations to understand your model and explain your hypothesis. But before the era of AI, we as the human were responsible for these step 3 and 4 that we have in the process of the science. When I talk about inferring, let's thinking about that this is related to understanding, so you want to understand the system, that's why you were collecting those data. And you are trying to discover some of those principles, which I refer to it as generalization. So we were that intelligent system indeed to be responsible for those steps. So nowadays how the AI has come is trying to probably, we are taking observations now and is trying to automate these steps. But are they really successful? That's the question. And in order to answer this, and in order to maybe I show you how I thinking about intelligent systems should be designed, I want to remind you that we should take into consideration these 3 steps that we as intelligent system might have been responsible for them. So is there any questions? So I wanted to actually make the session to be interactive, but feel free to stop me if you have any questions or any insights. So indeed we can turn this into a debate if you wish. All right. So we talked about science, we talked about some of the changes that were made. So let's take a closer look into what are these key principles that make intelligent systems useful for us, particularly for science. When I talk about science, you can also thinking about that the same principles can be applied to making it useful for healthcare, making it useful for any field that demands the same properties that as a scientist may demand from these systems. So I put some very narrow grayish color hint for you to probably answer what would be a useful science. And here we are going to go through 4 properties. So you have heard about it probably by a lot today. In this lecture, you're going to hear about it, or in any other lectures. But let's take us some pause and focus on these properties, because in my opinion, for us to really fully understand how AI is failing these and why we were not thinking about these properties before. So we used to use classical optimization, we used to use other technical tools to solve problems in science, and we never asked, are these techniques we use are reliable, are they interpreted? Why we were not asking those questions is what I today want to focus on. So let's go through these one by one. So in terms of reliability, the fact that you may not have that challenge is that technologies we used to have, they had performance guarantees. So maybe we did not invent that performance guarantees ourselves, or we did not know how an algorithm has convergence, but we knew when we are using a technology, for example, to detect some targets in space for defenses, or when we are looking into an MRI system or cardiac imaging, they're using some basic principles of physics that we all know that when we wake up tomorrow, they're still going to be there. So reliability indeed is important. So as I mentioned, if you were to develop a brain imaging system, you don't want it to only work in North America, you want it to be robust so that you can take it anywhere on the earth and still be usable. So reliability is an important aspect. Another aspect that indeed it's a very vague word, it's a notion of interpretability. It comes in many different places, so we can thinking about it in a way that the way the AI system is giving you an output, are they going through a reasoning that we as a human can understand? So it can be mathematical understanding, it can be human level understanding, and indeed they're not the case. Or a lot of time nowadays, for example, computational neuroscientists are spending time instead of understanding the science itself, to understand the AI they used to understand the science. So they're trying to understand how decisions are made, or what are the factors that is relying on. And so I will point to these factors why they're important. So I would like to mention that indeed there isn't, so these are not distinct sets, so they can be related to each other. But another thing that it has become quite important nowadays with the generative AI, that they can generate data for you, is the fact that are they relying on the same physical biological process or nature laws that that physical systems are relying on. So this is indeed very important. So the AI frameworks nowadays are not respecting these underlying properties that govern the data. And the last one is the notion of collaboration. So probably this is slightly a vague word for me. So when we talk about collaborations, you may thinking about you want a human in the loop to be able to evaluate the outputs of these AI systems. I'm going to touch on it in a slightly different way, in a way that you want these frameworks to be flexible, such that if you give it some input or if you give it some feedback, it reliably accepts that feedback and it's not giving you a contradiction as such. And I will elaborate on that in the next 20 minutes or so. So we may want to categorize things in slightly different things, but when I'm thinking about AI, here are the 4 important things that comes into play, and indeed they are intertwined in some of the challenges that we are facing nowadays. Okay, anyone here familiar with the Bloom's taxonomy? So we are looking into how AI systems learn. So why not to spend some time to thinking about when we teach a course, in what level of understanding we want human that are taking a course to understand and learn from any courses. So this is indeed the hierarchy of Bloom taxonomy, and any course that you might have taught or taken, they're trying to take you to the higher level of thinking skills. Instead of you trying to remember the names of a method, teachers, it's been a challenge for them to try to move you toward to be able to apply them, but not only apply, to be able to fully understand, such that you can analyze it, you can evaluate it, and create new things. So why not to push AI to the higher levels of these Bloom's taxonomy? Because if AI is all it's doing is to memorize, it won't be able to answer a hard question on an exam. So we should thinking about that we're teaching these AIs and how we should teach them these higher level and complex problems. Okay, so let's take a look into the reliability and how we can improve this property, or what are the problems that we are dealing with. So this is a graphics that it's actually not mine, and I forgot to put the credit here. it's one that when I started early on thinking about machine learning, it was around 2017, and we did not have LLMs or such, but this is what stick to my mind, such that you throw data more and more and more until it works. So, but can we rely on this process? So, and you can thinking about at the bottom we have this neural network. It's a complex model. You can think about it as a black box, such that you're not looking into these inner mechanisms, but only caring about what's giving you at the output. Comparing it with the top, such that if you were to use a well-known, understandable optimization model that is using, for example, some physical modeling of how gravity works, you have a very good understanding, and it has performance guarantees. However, this approach doesn't have that. And here I bring you that example that I earlier elaborate on that, such that this is indeed an active challenge right now for medical researchers, especially as more people are interested in accelerating these technologies such that we can have better imaging qualities from less data, such that patients' time can be decreased in an MRI machine, but at the same time we need to make sure that these systems are not going to be work only in one hospital. So why can't we rely on them? And this is related to some notions of interpretability. Any questions so far on that aspect? Okay. So how do we understand AI systems? So the field is called mechanistic interpretability. You train the network with a lot of data similar to that meme that I showed you. And then, so this is an important part, such that after it's trained, you try to probe it and see what it has learned. So I'm leaving with you here two different concepts that we don't necessarily need to go through them. You can either try to reverse engineer, or you can try to probe it to see what are the concepts that it has learned. So what can go wrong? So imagine we are in the vision case. So here I'm showing a Labrador face that is playing a guitar. And we use some interpretability techniques to tell us where is the Labrador. And it's pointing you that map that we see on the right. So there has been a lot of advancements. Maybe we call this success techniques, but this approach is not going to result in an AI system that is grounded in physics. So it may tell you how it has made its decision. For example, imagine that your network is doing a prediction task and is predicting that there is a husky in an image. So it has 100% accuracy. Every time you give it a Labrador and a husky, it recognizes that there is a husky over there. But when you tell it how did you do it, it's going to point into the snow. So what does this mean? So I did not make that up, so these images are slightly old, but what I'm trying to touch here on the subject that these AI frameworks are making spurious correlations. So the fact that we may open the black box and interpret them doesn't make them reliable, that they rely on correct causal factors. So the fact that we see a husky is not that there isn't snow. And this is indeed, in my opinion, and I'm a little bit biased on that, like one of the main challenges is related to this notion of spurious correlations and not looking into the causal factors as we do in science. We're trying to form an hypothesis and we're trying to infer the variables that are explaining our observations. And clearly with the form of predictions, AI systems are are being challenged on that. Okay, so now that we did this, let's slightly get into the notion of that physical plausibility. That was part of one of the 4 categories. And let me ask you this question. So imagine that I have trained this network such that it fill in the blanks and the missing pixels such that it give me a reconstruction or of this face before the box is in front of it. And I'm showing you 3 plausible faces. So do you think with your biological intelligence, you can tell me which one of those are the most plausible? I probably might have zoomed in for us to be able to see, but do you want to make a guess which one it is? Is the original or the most plausible explanation?
One on the left.
This one?
Yeah.
What is this? Okay, so actually it's quite plausible, but I'm going to choose this one as the plausible. But the practice that we are going through here is your brain has an inductive bias, and we sometimes calling it an internal world model of how a face should look like. So you can thinking about it in the same way that what are the inductive biases of these AI framework? How can I incorporate correct inductive biases? There has been a lot of research in machine learning, and like if you tell me you're using this architecture, like this way of training and all, like there's no ground truth. Like you can use any of these architectures or any of these approach, and maybe you're in science and you realize that there are 10 tools for you to analyze your data, and each of them may have different inductive biases. And it's important, if you really want to make sure that you rely on the outputs of these frameworks, we should choose the one, or at least design the one, that is respecting some of those let's say this time the biological processes that are underlying some, let's say, cell organisms that you're interested in analyzing its data. And let me actually give you another example. So a lot of time I put vision here because some of my research relates to this is the problem of inverse problem in vision, such that you can think about it, there is an original image that has gone through the process of missing pixels, and you're interested in performing a task of image restorations. But this physical plausibility, you can think about it in many different ways. Imagine that we have this network that is producing a time series of neural dynamics that are spiking data. So if the data that is generating, it may look pseudo-realistic to our eyes, but maybe we take a closer look and realize that there are two very close action potentials firing such that it contradicting to, let's say, the refractory periods of these neurons. So, and what that means, so this means that any output that comes out of that AI systems, it's not something you can trust, and it's not useful for you. Okay, so let me take you over another example that is trying to touch on the notion of physical plausibility. This time, this is an interesting paper. I put the title at the top if you would like to take a look, which is trying to raise a little bit of awareness on the challenges of foundation models. So we have heard probably a lot by now that in industry they're training these foundation large models similar to the language models that you may use, or some other foundation models that what they do is they try to feed a lot of data, a variety of it, and the architecture is scalable and expressive enough such that with enough data, hopefully they're going to start giving us the results that we have. So they looked into a lot of data from how a planetary system works. On the left, we are thinking about this is a true underlying model of how planets of the gravity directions should go when they're moving. And at the bottom there are the other planets that are similar, so let's take a look at the Earth. And on the right, they try to understand if that foundation model, aside from predicting that where the Earth is and how the Earth should move around the Sun, has some levels of understanding of this Newtonian equation. And what we see, it indeed shows that it has challenges. So what I'm trying to convey here is, if we're using these approaches for prediction tasks, it may give us a very high accuracy of predicting if I push something, it's going to move forward, but not being able to understanding the process themselves, or relying on some, I'm using the terminology of world models. You can search to know more about it in a way that you can think about that what is that underlying logical system that this AI is trying to use in order to predict. Okay, so let's go through this slide and then we make a small pause to see how we're doing so far. So last key, and I will expand on that, is the notion of collaboration. I briefly touched on this in the fact that AI frameworks are trying to do these prediction tasks, so they're not caring about understanding that causal factors, but one of the challenges that we may not be able to collaborate with them in a useful way is that humans do have different goals of studying something. So it's not about optimizing a loss functions on better predictions, but gaining insights on how a particular planet is supposed to be moving. But one of the key things that interests me is indeed on the notion of feedback. So can we give them feedback, and if we give them feedback, they can reliably incorporate that. What do I mean by that? So let's briefly take a look into one of the, probably I can say, subclass of AI that is being used a lot nowadays. We know them as generative AI. A particular one that I'm showing here, you can imagine that these are trained, so in this case they're trained on a variety of faces, such that when you tell it to give me an output, it's going to go through this sequential process of generating something that looks pleasing to you. So that's important. So it's going to give you something that it looks right. In terms of technicality, You can thinking about it that is sampling from some probabilistic distribution that is underlying your data. Okay, so, but generative AI is not useful on its own. What makes it useful is that if we can control them, and this is what I mean by the feedback, such that instead of generating, for example, a random molecular structure in drug discovery, so they're active research that they're trying to, for example, tell the system, generate these molecular structure with a particular energy or with these combinations, or generate a structure that has this particular effect and such. And I can tell you, if we were to do that, I want to make a statement here is that probably the next Nobel Prize is going to be go to those that can very reliably generate a molecular structure that maybe we were not being able to create, but construct on a paper that they should exist. I'm trying to emphasize that there is indeed a challenge in this control. And we might be able to see them, for example, for medical imaging. You can also thinking about those problems as a control, such that you may have limited number of measurements that you're taking from a knee in an MRI machine, but you're interested in enhancing that resolution. So you can tell this generative AI of generate a knee image for me that is high resolution of this low resolution version that I'm giving to you. So that input is a form of feedback. And it appears in here again I'm showing visions as it's easier to show on the graph, but it can go on variety of other applications. So let's go through something that probably is a little bit technical without going into the equation, but I think it's a key aspects and probably the key cause of these challenges that we see in AI today for controlling them. And this is a notion of disentanglement. So if you were to leave this room in an hour, if you only were to remember the fact that we are challenged, the AI is challenged with this disentanglement, entanglement problem, I think I would be happy, because that's probably one of the reasons. So let's take a look into the right first. So if you want to be able to have a control of this system, probably, or ideally speaking, these systems should have these different directions that you can choose to control them. For example, if you were to identify and disentangle two different directions, that if you move toward one direction, going to change the color, if you move into one another direction, it's going to change the shape what you see. You can call this a system that has disentangled in your knowledge of understanding a scene into factors that you have full control over them. So you don't want to be in a scenario that if you were to change the color, it's going to impact the shape. And for example, ideally speaking, you want to be able to have such control. So why this is important, getting again back to the molecular challenge that we said. If this system were truly able to form representations that had this property, and imagine that we could identify them. So if the color directions that we had here was looking exactly into the energy level of the molecules, we could easily play with the energy level without changing some other properties. And these are, you can, maybe next time you talk to an AI researcher, tell them this work, they get excited. Okay, so I'd like to make a pause here, just to see if the challenges we discussed were clear, and maybe which one of those you think is actually more important for your field of studies.
I think having the reliability and the interpretation for medicine is the most important. And I found that we're not there yet with the current AIs that we have. Like, even ones that are specifically aimed for the medical field, that are trained on medical literature, are very unreliable. Even simple things like interpreting literature they can't do, and even if you try to redirect them, they just like, I don't know, I found they can get confused sometimes. And so when it's not reliable, it's not usable. If you have to double check all the work yourself, it doesn't really help to have a good source. It's good for something, but
yeah, absolutely. I'm with you on that. So my question to you is, can we throw, because in industry they're trying to, or maybe that's their philosophy of how they think, they're trying to say data is the solution, the more data and more data. And so indeed, I was at a conference a year ago, and of course they did not say it directly, but the underlying information that I could hear from language model researchers were that they have trained these frameworks that we now use on all the available data that existed already. So they don't know what else to do, and we are still seeing them to be failed. So there indeed needs to be another solution. And so I would like to leave these two information with you, such that what they're trying to convey, what I'm trying to convey on the left is, there has been works in machine learning research that's showing that some useful things. So one is, even if you were to have infinite amount of data, the framework, the AI system that you may incorporate some structures or useful things or domain priors that you know, is always going to outperform the model that does not have that structure. So which is this red curve, and they have shown it like even in the infinite case. So the theories goes into that. And then you can also thinking about we're never going to have infinite computational resources. At every single line where you take a fixed amount of data, the framework that respects some of those causal underlying, or a network that have better inductive biases, is going to always perform better. And here I'm showing some other curves that we can thinking about. There has been projects that they try to put a camera. It's a baby view camera called. They're published online, and you can see such that they try to take everyday information the same way that babies are playing and learning from their environment, and to feed that to one of these very expressive architectures. And what they notice is that they're not scaling to the same level that a human does. So indeed we need, probably someone needs to calculate how many years it's going to be 10 to the power of 7 hours, but clearly it's not to the lifetime of a human, not even in the early years of a child that is learning. So this is basically, again, touching on this idea of probably we need more scientists or those that are in the fields that they need this interpretability and reliability to push the AI researchers that we need something that we know the data is not the solution. Okay, so now there were another keyword highlighted on my title, which we haven't touched yet, which relates to the brain. Probably this is the first audience that I'm talking to that they're much more expert than me about how the brain works. But let me tell you how, from perspective of someone that has trained as a signal processing electrical engineer and as a computational neuroscientist that's trying to understand algorithmically how the brain might be working. Okay, so we do get an image, and there's there are complex computations, and the questions that we have at hand is how these neural activities are forming a representation, let's calling it, that is a good explanations of an outside world such that we can use it for decision making and behavioral attributes. So, without waiting, let's go through the Bayesian brain hypothesis. So, have you heard of the Bayesian brain hypothesis? Okay, so then good, we're going to go through that. So, the way computational neuroscientists are thinking about some hypotheses about how particular perception works, not all 100% of them, we can think about it, a portion of neuroscientists have this perspective, such that our brain is having an implicit internal model of the world, how your face should look like, how these geometries are basically building a semantic understanding of a table, such that is trying to construct the best representation, some representation that explain the input data the best. And this process is referred to as active inference. So, isn't this similar to that we infer step or we model step of how science works? So we try to build a model that some variables maybe we infer are explaining our data the best. So, and you can think about that our brain is trying to do the same. The best representations that are fit the most the visual stimuli based on that internal work model. And without going into the technicality, when you were to, for example, go into these Bayesian settings of optimizing the representation, there are going to be some notions of feedback that you can thinking about. If the neural representations are not optimized for the particular input, they're going to be error communicated, and there are some active research that neuroscientists are trying to understand, for example, how prefrontal cortex are communicating some error communication with the lower levels of vision, where they're primarily their primary role is object recognition, for example. Okay, so how much time we have?
We have 18 and a half minutes left.
Okay, great. We're going to leave some time for questions as well. So, any questions about the Bayesian brain hypothesis? Okay. I should tell you, and probably by now you understood that I have a tendency of explaining things in slightly abstract way, that it might be challenging sometimes to grasp it, but I believe that certain problems actually need to get abstract out such that we can focus on the core principles. So it's intentional. This program delivery today is intentional. Okay, so now I'm going to confuse you a little bit, because the notion of inference that I talk about, they appear in a lot of problems that we want to solve. One problem here, again, I'm showing in the case of image restoration tasks, but they are under the category of inverse problems. And we will go through that together right now. So, when we want to solve the problem, we usually thinking about the data we have at hand, which is on the right, and we try to construct a goal. And the goal here is, I'm trying to fill in the missing pixels. So, but what a lot of AI researchers tend to miss is that before you even get the data, there was an underlying physical process between what you have measured and something that is, in this case, a clear image, or you can call it some causal underlying properties of that system that you're studying. So, what does this mean? So, when you were to start with a measurement, it's better to take into consideration a physical model that relates a clear image, and in this case it can be as simple as a linear kind of operations that you take the pixels out. MRI is the same, and I go through some other examples. And when you try to solve your problem, you aim to invert that process. This is a relation of the cause and an effect, and it goes into the philosophical notion of anything that we see is, you can think about it here, is a reflection of some underlying reality, and indeed it's up to discussions like if that underlying reality exists, because philosophically some line of thoughts are that there is no golden model of our world, and all models are wrong, for example, so we can maybe go through those aspects as we get to the end of the talk. But what I would like to take from here is that if you were to take into consideration that there was a forward model, and if you were to design a deep neural network or an AI system that takes you through this path, you better to incorporate those domain knowledges. Okay, so, and what I showed you was basically trying to explain in a technical way how the brain might be feeling and feeling those pixels. But there is another thing about the brain. So what I'm trying to argue here is, if we were to incorporate some of these basic principles about how we think the brain works, or the properties that so far we have seen, the notion of physical validity reliability, we do have a very robust perception, or interpretabilities are going to emerge in our AI system. So this is what I'm trying to argue here. So, for example, if you want a reliable system, you probably want it to represent your data in a semantic way. And indeed that's, again, this slide is usually for those that probably want to get an introduction about different properties of the visual system. But what's known about the structure of the visual processing system is that it has a topographical structure, that the neurons that are close to each other are usually fired together, and they are, in this case, for example, semantically incorporating similar information. So some of the indeed active research that I do is how we can design these systems that such properties are going to arise. And indeed, we have shown that it allows you to generalize better from less data, so it's not all about the data, and also to be more robust to the changes that it may come when you move your system from one environment to another environment. Okay, so let's get even more abstract. So now we're going to see something that's even more abstract. What am I showing here? This is one building block of a neural network. So the AI system, it's the simplest one that you can thinking about, that you process your data and they're inspired by neurons, and the neurons have these activation functions. So thinking about that there is a nonlinearity that exists in a basic building block. So what I'm trying to go here is, if we design this architecture such that their internal mechanism are trying to reason with that idea of inverse active inference and the Bayesian brain hypothesis that I talk about, they are going to have better logical reasoning. There are active research in large language models that they have shown that if we construct these systems that such that they do this iterative reasoning with some feedback and error corrections similar to the Bayesian brain hypothesis, their results are going to be much more reliable. So we can think about it in a similar way. Again, a lot of diagrams here, but what I would like you to take from here is, if we were to design this system such that there is some general notion of world model, that we look into some errors on how they are trying to recognize a scene and how they're trying to make reasoning, such that they get feedback from themselves and correct the errors that they're having. They're going to have brain-like processing and have their generalization. So this slide is for you. I intentionally made it empty, but we can fill it together. So what can we achieve? What can we achieve if the systems that we design are going to respect some of these general notions that I told you about, principles of how learning works in the brain?
I mean, if you can get an AI model to respect all those principles, and be reliable, then you can exponentially advance our knowledge. So in science, you can get an AI model to do the hypothesis generation, to interpret data, analyze data, come up with conclusions. Like, you can basically, it can be a researcher for you. Like,
Yeah. Well, you could fill in this slide much better than me. Exactly. So, like, So let me actually make a clarification here. So I'm not trying to make an argument because we have passed that stage of making biologically plausible AIs. Like for example, in 1950s, 60s, there were researchers that thinking about neural networks as how early layers of the visual systems are working, and they arise from that. Or there are many different ways of thinking about the current AI systems are not relevant. But I do think that there are key principles that we can learn about how the brain reasons, or maybe it's not only about the brain. Maybe it's my electrical engineer way of thinking about the brain, and that makes these principles useful. And incorporations of those key principles. So you shouldn't necessarily one-to-one connection. Okay, so I talked a lot. I put the notion of an inverse problem several slides back. So let's actually change gear, and here I wanted to show you a few of problems that are referred to as inverse problem that I have personally worked on before on the image restoration tasks. And a part of my research that I have interest on is helping neuroscientists they measure neural activity to enhance their understanding of properties of those neural activities or some regions of the brain. Problems in neuroscience can be casted as inverse problem. A lot of computational imaging. They are the basic principles of how that image can be constructed of a black hole is based on the notion of inverse problem. Actually, I did not work on that. So, and then in seismology, and also some medical imaging that I have worked before, and engineering as well. You can imagine that you send some radar systems into the space, and you get reflections from some targets. And to inferring the locations of those targets is an inverse problem that you can thinking about. Okay, so using these principles that I today talked about, it allows you to have more efficient architectures. It allows you to, for example, have less data, so you're decreasing the compute, you're decreasing the need of the data for better performances. But it allows you to introduce some notion of interpretability. And I believe, I mean, as you mentioned, like maybe reliability and interpretability is one of the most useful properties. So, before we end the session, so let me briefly take you over the inverse problem of that you consider in computational neuroscience. So there are a variety of stimuli that stimulate the brain. Like in this case, for example, you have some naturalistic experiment set up where the mice is moving around and interacting with a variety of objects, and it might be visual, it might be smell, and you collect data. So we are in that, we observe. So given the neural activity, we are interested in detecting the particular features that the neurons are responding to. So what are those aspects of the environment that a dopamine neuron, for example, is caring about, how it's encoding it, and characterize that. So that's the problem that interests. So with the tools that indeed I showed you, so we can use these AI systems that, for example, here with the help of my my collaborators, we looked into dopamine neurons, and we were able to extract interpretable representations such that one of the representation spaces were corresponding to the type of the trials that the animal had been in these experiments, and another one to the amount of the reward that has been given. So, and the other one is related to a neuroscientist were trying to understand the role of understand the neural computations in the ventral and dorsal stratum to understand how the reward is encoded. And with this interpretability, she actually used our tools for some hypothesis testing. It's not published yet, but it's some of the collaborations that we do hope. Yeah, this is the end of today's session. So I hope you probably get to know how I'm thinking about the key properties that AI systems should have, but also about this niche angle of interpretability with these disentanglements that I told you about.
So you know, this really adds to the course in the sense that it doesn't really overlap at all with what the other AI lecturers talk about. So you're kind of in your own world, you know, and no, that's great. We needed this, you know. Every time I ask the students, you know, a course about the future has to morph and change all the time or it's not valid, right? So what should we add? And they never suggest anything specific. But the lecturers themselves, if you ask somebody new, they will bring us something that we didn't know that we needed, but now we see that. So we need your content and your point of view and your vantage point is good for the students. And so what I guarantee them is this course has survival value in the long run. When the future comes, you know, we'll talk about enough scenarios and ways of thinking about it that they'll be more mentally prepared than their colleagues, because there's nothing the future can throw at them that they haven't thought about in some sense in this course. So you're kind of adding to that, thinking about other parameters of success and how to think about what we want from AI. Yeah.
Yeah, probably you're not gonna hear about this anywhere else, but I think it's important to sometimes talking about this intersection, because I don't want to come give a talk that it talks about the applicability of a method for those that are trying to use, but indeed to dive a little bit about promoting communication between those that are using the tools for applications and those that are designing, and perhaps can maybe give you a little bit more insights that how we're thinking about those challenges from a technical perspective.
So I think that talking about scale, if you look at all the scientific presentations out there, both in AI and outside, very few are really focused on scale. But if you look at AI presentations in any one city or institution, you find that everybody's proud of what they're doing. And the reason for that, nobody's confronting them. Like, if they describe a study that really only impacts 10 patients, and you know it's possible to do work in the same area that impacts everybody in the world, so yeah, like 8.5 billion. They never worry about that because they never question their worldview. You know, they're working within a certain realm. They get data, it's successful, they prove things. And I think for the people whose worldview is very small, That's kind of the way they think about things in general, that it's not trying to change the world. That's crazy. Why would you ever think about doing that? But what we're doing here in Edmonton, is it as good as what they're doing in Calgary or Winnipeg, you know? Or what we're doing at this institution, the University of Alberta, is it good? So on and so forth. So everybody can feel this intrinsic pride in the quality of what they're doing, even if the impact of what they're doing is practically zero. You know, that this model that they're using would not apply anywhere else. The N is too small to prove things. Anyway, yeah.
Well, so to complement your perspective, I do think these localized efforts and optimizations do actually propagate, like their impact propagates globally.
Right. Yeah.
So, like things that are being done here in Edmonton or in some other cities. Probably with more communication and like to hearing criticism of that local optimization can be helpful.
But in medicine, you can see this play out in transplantation, which is kind of my field. The clinical practice is really a failed enterprise because we only reach 5% of the people who need an organ. They have end-stage disease, they need an organ. Most die waiting for an organ that never comes, right? Because we're only reaching 5%. But the people doing research within that existing cadre of the transplanted patients can show that they're improving various characteristics of that 5% that we're actually treating. It's getting better and the patients feel better. And, yeah, and they can work their entire career there, never worrying about the other 95% that never not reach it. You know? So, and I think this happens all the time. That's just the part of medicine that I know best. But that same sort of thing, it's one of the reasons you even now are aware that I'm a poet and have spent, people say I'm a physician during the daytime, poet at night. Why did I do that? When I was just teaching medical students, I thought, this isn't really respectable because this is an elite group of humans. And I'm like focusing all my effort on this elite group of humans. So what I found is another similar age group of humans, which is at-risk youth that came to this Tuesday night poetry. And they're not in medical school, but the same age. They're people with completely different problems. When they leave the house, they're immediately at risk because the way they look is a way that other people know what no one should ever look like that. So yeah, and so their poetry is so good because their lives are so imperiled all the time, right? And so I created the infrastructure, I shot video of their poetry and created lighting and sound and stuff like that. So what's the difference between teaching medical students and doing something like that? Well, the one thing I only tried once, and I realized I should never do this again. If somebody wants a ride home, say no. Because the one time I said yes, it's the scariest evening ever. I didn't know there were parts of this city that are so marginal. It's where we ended up where this person lived. And I could see them in their mind all the time during the drive. They're thinking, well, Dr. Solis is taking me home tonight, but where could this go? So, okay, You can't apply it when you have an elite group of well-behaving students and then another, but still, to put the two together and to do things as a physician in a setting where no other physicians are there ever, maybe no academics are there, no people older than 30 are there, right? It's just, it brings a certain balance to life that you feel, okay, overall, I'm behaving in a reasonable fashion. I'm not just helping people who are already or sort of leading an upscaled, positive outlook to life. I'm also dealing with people at the other side, right? And you may wonder, well, Kim, are you still doing that? No, let me tell you what happened in 2019. 2019 is before COVID, right? So the leader of this spoken word poetry initiative is a really well-known Nigerian poet who used to actually be like the poet laureate of that country. And we would have young people coming who were so high from drugs, they would arrive, they couldn't even speak, right? And she's thinking, well, you know, my career, all these wonderful things that I've done for the government of Nigeria, so why should I have to put up with this? So in late 2019, and you realize historically COVID existed, it just, nobody had really discovered it yet. And so we stopped poetry in late 2019, and then in February, March 2020, when COVID came, you know, it seemed like we had stopped because of COVID, but that isn't what happened. So yeah, there isn't such a thing any, now that COVID's sort of over, the poetry hasn't started up again. And yeah, so it's strangely connected to large societal issues. But I feel much happier talking about what I do when you realize that a lot of the poetry that I was a part of was not in a medical student setting, you know? And I was the only one talking about technology and AI. Who writes poetry about that? I do, right? But everybody else is talking about love and loss and the usual poetry. So, yeah, so that's the deal. So, and I spend most of my time sort of working on planning things related to this course. So if you think about it, everything that I do in some way is related to this course. So even when we only have 3 students, that doesn't really matter. It's not that the course is only valuable, but we have a large, so the course maxes out at 13. The way it's currently structured, we can't have more than that number. Yeah. And you may wonder about the exams. These guys have an exam coming up. The exam is open book, open computer, everything. But we want to do it in a semi-controlled setting, so I want to be there and the TAs are there. And we don't want to disadvantage people who have no background or have extended background. So the time of the exam, they don't have to be there for the whole time, is 2 hours, 50 minutes. That's a long exam. But the exam only takes like 1 hour to do. But if they want, they can spend the whole time. And the interest is generally nobody leaves. And that's because of Shauna Panja. She's sort of a physician astronaut. She's going to space in 2026. And she gives extensive feedback on her part of the course. So the more they write, the more they get feedback from this charismatic young woman who's going to space next year and who can tell you why space is trying to kill you. So you kind of feel the longer you spend, once you finish every other part of the exam, the more time you spend on Shauna's question, the more you'll get back from her in feedback. So that's,
So write as much as you can.
that's how it works. Yeah. So thank you very much. I intend to invite you back over and over again, and yeah, that's the other thing. So
We'll probably cover something else, even to the
yes, yes, no, we can keep talking about other things, sure, that would be fine. You don't have to ever talk about this subject again, or you could. Yeah. And so you may wonder who owns this course, because most courses, the university owns the content, right? And think about that. If you give a course, would you want to own the content yourself? Well, at a certain point, this course had controversial enough content. It's entirely speculative, right? It's about things that don't exist now, but presumably will in the future. And so there was an issue of New Trail, the university alumni magazine, in winter 2015 about the course. And some high official, I don't know, the university president or somebody, was so disquieted by looking at the beautiful graphics that we had of like AI leading humans on leashes sort of thing. We didn't really say, there was some speculation about where China might fit in the world, and about the edible arm. That's probably the most, and I have nothing to do with this. The university PR arm, which is immense resources compared to me, they put that issue of New Trail together. Yeah. And because of that, anyway, to make a long story short, the university and the faculty of medicine decided to give me the intellectual rights to the course because they didn't want it. But they wanted to make sure that the students would always have access. So even though I own the course, I can't shut the university access to the course off. I have, yeah, so that's the way it currently sits. Yeah.
So this is the only course that has that privilege, probably.
Yeah. And if you go into New Trail, you'll find that you can readily get every issue of New Trail going back to just the one before winter 2015. So they tried to make it look like, it just, they couldn't make them all available. Yeah, so, but they made the PDF of that issue available to me, so I can provide it. They just don't want, as a university, being responsible for this thing like the edible arm. You're out in the woods and you're hungry, so you eat your own arm and then it regrows and so on. Yeah, these are ideas that Kim Solis did not come up with. They were created by the public relations arm of the university. So anyway, okay, well, I hope when I invite you back that you want to come back, and of course there'll be.
Yeah, absolutely. I'm happy to come back again.
Good. Okay.
Yeah.
And you're welcome to attend by Zoom on Thursday if you want for my AMA, if that's of interest to you. And also you don't have to.
Yeah, absolutely. So if I don't have a meeting, I will definitely.
Cool.
Yeah,
Cool.
I will be happy to.
Okay. Excellent. Yeah, so there's no face-to-face class on Thursday. It's only by Zoom. Yeah.
So our paper topics and mentors are due this week on Thursday?